Okay, in this slide, I will present a MOLED wavelet EXAFS developed by Funke and new wavelet EXAFS developed by us. The mimic signal with 3 points is made using this equation, which are 3.6, 3.10, and 4.10. We would like to prepare the resolution between MOLED wavelet and new wavelet called superlet. Each EXAFS as a function of k or r has a limitation of resolution like this figure. The EXAFS in k-space doesn't distinguish different bonding lengths in the same k-space. in the same k. Whereas the EXAFS in R space doesn't distinguish different k in the same R. In new wavelet transforms, PCM is defined as 2 pi cm over KSD and Rm. The new wavelet transform EXAFS uses the multiplication of MOLED wavelet, which is indicated as a superlet. The wavelet transform is accomplished by geometric mean by Mocha error. MOLED wavelet transform is controlled by Rm 3, 4, 5, 6, while the new wavelet transform EXAFS is adjusted by the number of cycling and the order of geometric mean. MOLED wavelet transform can't distinguish 3 points simultaneously, as you see. Whereas the new wavelet transform developed by us can distinguish 3 points, which means that our new wavelet transform has a higher resolution than previous one. From now on, all the wavelet transforms will be performed by this new method. To check atomic discriminations, we generated theoretical EXAFS in k-space using PEP. The atomic models with 1 atom and 2 atoms at the same bonding length, 2.76 angstrom probing PT, are prepared respectively as shown in each figure. The atomic backscattering amplitude FKR and the phase shift pi kr in these equations depends on k-space. The left figure shows EXAFS as a function of k, and the right figure is EXAFS as a function of r. Also, we prepared the contribution of adjacent atoms of titanium at 2.76 angstrom and copper at 3 angstrom. The wavelet transform EXAFS was obtained at k weight with 2, the number of cycle 9, the order 6. The wavelet transform EXAFS of titanium and copper are very similar, whereas those of zirconium and platinum are considerably different, which means that the atomic discrimination is possible by the wavelet transforms when the difference of atomic number between two atoms is a little bit big. The wavelet transform EXAFS visually reveals the atomic discrimination of two atoms at the same distance from a probing atom. Comparing the wavelet transform EXAFS of platinum titanium and owning titanium, or platinum copper and owning copper, you can see the contribution of platinum. The discrimination between platinum and zirconium is clearly shown by the wavelet transform EXAFS. The difference of bonding lengths for titanium and copper can also be described by the wavelet transform EXAFS. To apply practical systems, we prepared the platinum nanoparticles on titanium oxide and zirconium oxide supports as shown in these figures. The EDS, high resolution TEM, and XRD show that tiny platinum nanoparticles are distributed on titanium oxide and zirconium oxide supports. However, they doesn't demonstrate which one is platinum or titanium or zirconium. You can see the wavelet transform EXAFS to the quantum maps of platinum foil, platinum nanoparticles on titanium oxide support, and platinum nanoparticles on zirconium oxide support. These wavelet transform EXAFS are obtained from EXAFS in K-space at a probing platinum atom with K weight 2. Comparing to platinum foil, the wavelet EXAFS of platinum nanoparticles on supports are different. The wavelet transform EXAFS demonstrate there are some platinum oxide bonding and some platinum titanium or platinum zirconium bondings. When the signals obtained from data feeding is removed, the oxygen and metal signal in wavelet transform EXAFS are revealed as shown in this figure. We address the position of platinum atoms on titanium oxide supports using DFT calculation. The this result validated that the platinum oxides are stable on oxidized titanium oxide. The wavelet transform EXAFS quantum maps in this figure is well in agreement with the previous result, which is DFT calculation. The data fitting results, you can see these tables, are shown in the table and the figure. As you know, to get exact local structure information, we must have the fitting processing. However, we can visually check structural information in wavelet transform EXAFS, including atomic discrimination in advanced fitting data to model. The result revealed that there are some oxygen atoms, you can see, some titanium or zirconium around the platinum atom. Also, neighboring platinum atoms are located around the probing atoms. From the result of data fitting and wavelet EXAFS, we can make the platinum cluster model like this figure. Next, let me demonstrate the zinc oxide cross mechanism with the wavelet transform EXAFS and Fourier transform EXAFS. We synthesize the zinc oxide nanostructure with the zinc nitrate and hexamethylene tetraamine, which is referred HMT in figure 1. Zinc oxide solution is zinc nitrate solution at room temperature. And then zinc oxide HMT solution 1 is zinc nitrate and HMT solution at room temperature. Zinc oxide HMT solution 2 is a solution of zinc oxide HMT solution 1 at 80 Celsius. Zinc oxide HMT solution 3 is a solution of zinc oxide HMT solution 1 at 80 Celsius in 10 minutes. Then we obtained the zinc oxide precipitate on the bottom and zinc oxide nanostructure in 1 day. The structural changes in the solutions are described as GENS and EXAFS in our space. We already analyzed the zinc oxide cross mechanism in this figure. This paper. Now we can understand that the second peaks in EXAFS in R space indicate the zinc pairs. However, when I first checked this data, when I meet this data, I didn't understand whether the second peaks is in the second peaks in solution samples zinc pair or not. Combining DFT calculations, we made the zinc oxide growth mechanisms in the solution as shown in the figures. The wavelet transform EXAFS is obtained from EXAFS in case space with K weight 3, number of cycle 9, and maximum order 6. The wavelet transform EXAFS visually reveals the change of zinc-zinc pairs. You can see the atomic discrimination of oxygen and zinc. The site of zinc atoms from a probing atom in wavelet transform EXAFS is located at higher than that of oxygen atoms in K-space. This table demonstrates the fit result of EXAFS at zinc KH. This result will correspond to the wavelet transform EXAFS. Especially, the zinc-zinc pairs in wachite structure indicate the crystallization of zinc oxide. When we use the wavelet transform EXAFS as a complementary for fittings, we can make a goodness of fit. As a final examples, I prepared vanadium molybdenum oxide nitrogen on graphene as shown in this figure. The EXAFS data are collected at vanadium KH and molybdenum KH respectively to investigate the local structure. To understand the add atoms for nitrogen, carbon, vanadium, and molybdenum, we made a theoretical wavelet transform EXAFS for them using PEP. The wavelet transform EXAFS signals of nitrogen and carbon are near 3, 4 inverse angstrom, whereas those of vanadium and molybdenum are located around 6, 7 inverse angstrom. Comparing to theoretical wavelet transform EXAFS, we can find atomic properties such as the wavelet transform EXAFS at molybdenum and vanadium KH respectively. Now, let me introduce JWT EXAFS software, which is made by me. The wavelet transform EXAFS in this software is based on separate as shown in this equation. The number of the NC is the number of cycle. O mean is the first order in separate. O max is the last order. You can control mesh of to the quantum map using mesh card. If you reduce the mesh, you can see the wavelet transform EXAFS in short time, but the resolution of wavelet transform decreases. The data files are input by import card, and their amplitude can increase or decrease using weight ratio. Run PEP is not worked in these softwares. If you install LATS within Python, then you can use it. So I open JWT EXAFS, and then you can see. So import the which you want, and you can find the data. In my case, I'm importing theoretical oxide and titanium and platinums. Okay, so and then let me show you the data using open file. Click and then anyone choose. Yeah, in my case, oxide. Okay, so you can see the data and the k space, and then chi, k weight 1, 2, 3. We use these ones. Okay, second column. And then I wanna fix the change the k range and r range. Yeah, k range and 2.5 and k max and 11, and then weight maybe 3. It's okay. And then the r space and the r maximum also 4. So let's check the data, and then you click the data, and then you can see the graph. And if you want to change the data, and you change the weight, I change the weight of oxygen 0, and also titanium Ti 1. Then also, and click the data, so you can see the EXAFS in K space. It's like that. So, and if you want to change the Fourier transforms, and then you click the FFT buttons, and you can see it's right. Okay, and then also if you change the state, converting Fourier transforms, and you click the but you want to change the mesh, and you can put the mesh rate. One is default, and then 0.3, and the mesh is decreasing. Okay, so you click the wavelet, and then you can see you're waiting a few times, so you can see the wavelet transform EXAFS in titanium. And then if you want to see K space, R space, and wavelet, and then you click all, you can see all things simultaneously. Okay, you're waiting. Okay, like this. Okay, then I close the everything. Okay, then if you want to mix the oxide and titanium and platinum signals, and you can give the weight 1 and 1. In my case, 1, 1, 1. But it depends on you. So, you can change them. So you collect the data, and then you can see combine the result. Okay, so also FFT, you can see these like that, and then wavelet transforms, and then in my here's wavelet transform, and okay, you see, right? Okay, also if you want to save data and Fourier transform and wavelet transforms, you can click these buttons. Okay, and then if you want to calculate the theoretical path, and frankly, you click here, but in this JWT EXAFS, we don't have the programs long path. But if you install lots with Python, then you can use this one. Not now, okay? Okay. Thank you for listening and for able transform lecture. Yeah. See you next time.